A safe flyby sounds like the end of the story. On April 13th, 2029, it will be the beginning. Long before Apophis reaches Earth, observatories around the world will already be watching. Radar dishes swing toward the sky. Telescope domes begin to open, one after another. Not because anyone expects an impact. That question has already been answered. Apophis will miss Earth. The calculations leave no doubt. But they also point to something far more unusual. The encounter itself. The space around Earth is anything but empty. Invisible highways surround the planet. Thousands of satellites travel through them every day. Some circle only a few hundred kilometers overhead. Others orbit much farther out. One narrow ring hangs almost perfectly above the equator. From the ground, the satellites there seem almost motionless. That distant belt quietly carries weather forecasts, television broadcasts, phone calls, and much of the communication modern life depends on. Now place two distances beside each other. 35,786 kilometers. 31,600 kilometers. The satellites occupy the first. Apophis passes through the second. Seen from the side, the geometry becomes surprisingly simple. Earth sits at the center. The geostationary ring circles high above the equator. Another path enters the frame. The asteroid falls toward Earth, passes beneath the ring, then climbs away again. Nothing touches. Nothing collides. Everything unfolds exactly as the calculations predict. But every kilometer closer gives Earth's gravity a little more influence. Not enough to capture the asteroid. Enough to make the encounter itself the real event. The flyby will last only a few hours. Apophis will continue around the sun. Earth will continue around the sun. From a distance, it will seem as though almost nothing happened. The measurements will tell a different story. Not during the approach, after it. For decades, asteroids have crossed Earth's orbit. Some passed much farther away. Others came even closer. Most slipped back into deep space with little more than another entry in an astronomical catalog. Apophis is different. Not because it is the largest. Not because it is the most dangerous. Because this time, scientists can watch the encounter change the asteroid itself. The radar dishes are not waiting for Apophis to arrive. They are waiting for it to leave. At first, every image will look familiar. The same elongated body. The same uneven surface. The same asteroid moving safely beyond Earth. Place those images side by side. The asteroid still looks the same. Then add another. Almost the same. Almost ... The changes scientists expect are too small to leap out of a photograph. A mountain will not become a valley. The asteroid will not split apart. Instead, loose boulders may settle into new positions. Dust may slide where gravity briefly changes direction. Rock buried for millions of years may suddenly be exposed to space for the first time. Nothing explodes. Nothing shatters. Apophis simply leaves Earth looking slightly different than when it arrived. Those changes begin long before anyone can explain them. As the asteroid falls deeper into Earth's gravitational field, the side facing Earth feels a slightly stronger pull than the far side. The difference is tiny. Across an object only a few hundred meters wide. Earth's gravity changes by only a small amount. For a mountain on Earth, that difference would hardly matter. For an asteroid held together mostly by its own weak gravity, it can matter a great deal. The force does not arrive all at once. Every minute toward Earth makes it a little stronger. Every minute afterward makes it a little weaker. Apophis will cross that invisible gradient only once. The experiment cannot be repeated. Watch the asteroid arrive. Watch it leave. The path will look almost identical. The object may not. That is why so many telescopes will be looking at exactly the same point in the sky. Not to witness a collision. Not to find out whether Earth survives. Those answers already exist. They are waiting for the first images taken after the flyby. The place beside the last images taken before it. Only then will Apophis begin to reveal whether Earth's gravity left its mark. The first photographs will not answer that question. Neither will the second. Or the third. A single image can tell us where Apophis is. Only a long sequence can tell us whether it has changed. That is why radar becomes just as important as the cameras. A photograph captures reflected sunlight. Radar creates its own light. It sends a signal toward the asteroid, then waits for the echo. Every returning pulse carries another measurement. Distance. Rotation. Orientation. Even the asteroid's shape as it slowly turns through space. Before the flyby, those measurements establish a baseline. Apophis rotates this way. Its surface reflects radar this way. Its spin repeats with the same steady rhythm. Nothing unusual appears. Then Earth intervenes. The flyby ends. The asteroid pulls away. The radar begins again. The same object. The same instruments. The same measurements. Now place the two datasets side by side. If nothing changed, the echoes should repeat the same pattern. If Earth's gravity altered the asteroid, the difference appears immediately. Its rotation may no longer repeat at exactly the same speed. Its long axis may point in a slightly different direction. Even the rhythm of the returning echoes may shift. The asteroid does not have to break apart. It only has to spin differently than it did before. That possibility is what makes this encounter so valuable. Not because scientists expect something dramatic, because they expect something measurable. There is an important difference. A loose pile of rock rarely announces that it has shifted. It keeps almost the same shape. It follows almost the same path. Only careful measurements reveal that something inside has settled into a new arrangement. The photographs still show the same elongated asteroid. The radar keeps returning echoes. But place today's measurements beside tomorrow's, and a new picture begins to emerge. Apophis arrived with one rotation. It may leave with another. Its surface arrived carrying rock that had remained hidden for millions of years. It may leave with fresh material exposed to space for the first time. The flyby itself lasts only a few hours. The comparison lasts much longer. Every radar echo, every light curve, every new photograph, each one is matched against observations made before the encounter. The asteroid keeps moving away. The measurements keep following. Because the question is no longer where Apophis is. The question is whether it is still exactly the same object that entered Earth's gravity only hours earlier. The asteroid does not need to change very much, only enough for the instruments to detect it. And that possibility reaches far beyond Apophis. Every orbital prediction begins with a simple assumption. The object leaving today is the same object that arrived yesterday. Its position changes. Its speed changes. But the object itself does not. For most asteroids, that assumption works remarkably well. Apophis gives scientists a rare chance to test it. If Earth's gravity shifts loose boulders across the surface, if the asteroid's rotation changes, even slightly, if it begins tumbling in a new way, then every future prediction has to begin from a different starting point. The change may be subtle. Its consequences are not. Before the flyby, Apophis follows a familiar path around the Sun. One orbit takes 324 days. It belongs to the Aten family of near-Earth asteroids, spending most of its time inside Earth's orbit. Now watch the encounter. The asteroid falls toward Earth, passes beneath the geostationary ring, then climbs away again. The flyby ends. Now compare the old orbit with the new one. The difference does not appear near Earth. It appears around the Sun. The path has shifted outward. One orbit now takes about 423 days. Apophis no longer spends most of its time inside Earth's orbit. It joins a different family of near-Earth asteroids. No rockets fired. No engines burned. One pass through Earth's gravity was enough. Nothing about the flyby looked dramatic. No explosion marked the moment. No visible boundary separated the old orbit from the new one. The entire change existed in motion. Apophis left Earth carrying a different future than the one it arrived with. That future can be calculated. But first, it has to be measured. Every observation after the flyby becomes part of that measurement. Every radar echo. Every light curve. Every new position against the background stars. Each one asks the same question. Not whether Apophis will strike Earth in 2029. That answer has never changed. The question is whether the asteroid leaving Earth's gravity is following exactly the path we expect, or one that became just a little different during those few hours. A tiny difference, measured over a single hour, can grow into thousands of kilometers after years in orbit. Not because the asteroid keeps changing, because motion never stops adding up. The flyby lasts one night. The new orbit lasts for decades. And a new orbit changes more than a calendar. It changes where the asteroid will be years from now. Every close approach begins long before an asteroid reaches Earth. It begins with thousands of earlier trips around the Sun. Each orbit leaves the asteroid in a slightly different place. Each one subtly changes the geometry of the next encounter. Small differences accumulate. Orbit after orbit. Year after year. That is why the story does not end when Apophis disappears back into the darkness. The flyby continues inside every calculation that follows. The asteroid will never return along exactly the same path. Every future prediction begins from a new starting point. That is what planetary defense teams are really watching. Not simply a successful flyby. But the moment the reference itself changes, picture drawing a straight line across a sheet of paper. Now move the starting point by the width of a pencil. At first, the two lines almost overlap. Keep drawing. The gap slowly widens. By the edge of the page, they no longer end in the same place. An orbit behaves much the same way. A tiny change during one close encounter never stays tiny forever. Each trip around the sun carries it farther. Then farther still. The asteroid does nothing. Motion does all the work. That is why every measurement made during the 2029 flyby matters. Not because Earth is in danger. It is not. Not because Apophis suddenly becomes unpredictable. It does not. The encounter will make this asteroid better understood than almost any close approach before it. For the first time, scientists will watch a known asteroid pass this close to Earth using modern radar, precision optical tracking, and a spacecraft already preparing to meet it after the flyby. The same object will be measured before the encounter, during it, and after it. The comparison is the experiment. No laboratory on Earth can recreate an asteroid crossing a planet's gravity at several kilometers per second. No simulation can replace measurements taken from the real event. The flyby happens once. The data will remain long after it is over. Years from now, another asteroid will approach Earth. Its orbit will be calculated. Its rotation will be measured. Its future path will be projected decades ahead. Some of those methods will trace directly back to Apophis. Not because Apophis was the most dangerous asteroid ever discovered, because it became one of the rare opportunities to watch gravity reshape an asteroid in real time. Look again at the corridor of space where the encounter will happen. Nothing marks it. No glowing boundary surrounds Earth. No invisible wall waits for incoming asteroids. Apophis enters. Apophis leaves. The corridor remains exactly the same. Only one thing is different. The asteroid that emerges is no longer following exactly the same future as the one that entered. By the time Apophis passes Earth, one question will already be settled. It will not hit the planet. Another question will only be beginning. How much can a single encounter change everything that comes after? The answer belongs to far more than Apophis. Every asteroid discovered in the future will pass through the same chain of measurements. A telescope finds it. Another telescope measures it again. Its orbit becomes more precise. Its future grows easier to predict. Most asteroids never offer a chance to test those predictions so closely. Apophis does. For a few remarkable hours, prediction gives way to observation. Scientists will stop asking what gravity should do. They will watch what gravity actually does. The asteroid becomes the measurement. The flyby becomes the experiment. That is why observatories around the world have been preparing years in advance. Ground-based radar, optical telescopes, and a spacecraft already changing course to meet Apophis after the encounter. Each instrument measures something different. One tracks the orbit. Another records the changing brightness as the asteroid spins. Radar maps its shape and rotation. The spacecraft will later compare the surface that arrived with the surface that departed. No single observation tells the whole story. Together, they can. One image captures the asteroid before Earth. Another captures it after. One radar echo returns before closest approach. Another returns afterward. One light curve belongs to the old rotation. Another belongs to the new one. Each comparison asks the same quiet question. Did anything change? The answer will not arrive in a single observation. It will accumulate. One measurement agrees, then another, Eventually, one begins to drift. Slowly, the flyby stops looking like a close approach and becomes a reference point. Future asteroid missions will return to these measurements. Future orbital models will be tested against them. Future predictions will begin here. Not because Apophis was uniquely dangerous, because scientists watched reality at the exact moment gravity had the chance to rewrite it. Look one last time at the path through Earth's gravitational corridor. Nothing marks where the encounter begins. Nothing marks where it ends. The asteroid enters. The asteroid leaves. Earth continues around the Sun. Apophis continues around the Sun. From a distance, the solar system looks exactly as it did before. Only the measurements remember that anything happened. A safe flyby was never the end of the story. It was the moment the story became measurable.